In the last video, we discussed the molecular orbital diagram energies for the second row diatomic molecules. And we indicated that there was a difference between the diagrams when we go from nitrogen to oxygen. So this video is going to attempt to explain that difference. So as we move from left to right in the periodic table, we add protons to the nucleus. And we're increasing the effective nuclear charge. In doing so, the 1s and 2s orbitals are influenced strongly, and the 2p orbital is affected slightly. So if we look at what happens to the energies as we go across from lithium to beryllium to boron to carbon to nitrogen to oxygen to fluorine, we can look at the relative energies of the 2p and the 2s orbitals. Okay, remember the nucleus and the number of protons are down here. For lithium, there's going to be 3 protons. For beryllium, we have 4 protons. So what happens is these protons are pulling a little bit harder and a little bit stronger on the 2s, and the 2p is relatively unaffected. So this 2s orbital gets a little bit closer to the nucleus. In boron, we have 5 protons down here. So the 2s orbitals are going to be influenced a little bit stronger, whereas the 2p, again, aren't going to be very much affected. With carbon, there's 6 protons. So the 2s orbital gets even closer, and the 2p is slightly changed. Nitrogen has 7 protons in the nucleus, and this 2s orbital is going to be influenced even more greatly. With oxygen, we have an even more dramatic effect because there's 8 protons in the nucleus. And for fluorine, which contains 9 protons, we're going to get an effect that looks like this. So what we see happening is the delta E, or the change in energy between the 2s and the 2p orbital, is going to increase as we go from left to right in the periodic table. Okay, so in everything to the left of this dotted line that I occur, and remember before we do this explanation that we can have the 2s and the 2p orbitals mixed together or hybridize. So what happens is, over here in this case on the left-hand side of the line, we can say that sp mixing occurs. And in a molecular orbital sense, we say mixing instead of hybridization. On the right-hand side, we have no sp mixing because the energies of the s and p are too large. So we aren't going to see any type of mixing occur over here on the right-hand side, and this is going to influence our molecular orbital diagrams. So for O2 and F2, versus nitrogen and everything to the left, we're going to see a difference in the molecular orbital diagram. So the center energies of our molecular orbital diagram, just looking at the molecular orbitals, is we're going to have the sigma and the sigma star. Then we're going to have orbital energies that look like this, where we have another sigma down here, a sigma star, a pi, and a pi star for these energies of the nitrogen and everything to the left in the second period. Then for oxygen and fluorine, we're going to have our sigma and our sigma star, but the other sigma is going to be down here, pi, pi star, and sigma star. So these are the relative energies of that center portion of the molecular orbital diagram. And over here we have sp mixing and no sp mixing. And this is going to result in the differences of the molecular orbital diagram energies for our second row diatomic molecules.